We'll now take a look at an example of designing a circuit. In particular, we're going to look at how we would add numbers using a circuit. So what we're going to do here is we're going to perform binary addition on two unsigned n-bit integers. There could be some other variations, but we're going to try to make this as simple as possible. And this particular type of circuit has a name. It's called a full adder. And the way we're going to do this is we're going to break it down into two parts. So the first part is that we're going to construct a circuit that's called one add. And what this does is it just adds a single pair of binary digits and the carry digits. That's all. It's just going to be a circuit that deals with a single set of respective binary digits for the two numbers. And then the second part is that we'll connect all of the one add circuits. So there'll be n one add circuits because we have one for each digit for our numbers. So we'll have n one add circuits, and we'll construct an n-bit full adder circuit. So before we can design our circuit, we need to know what are the inputs and outputs for this circuit. Well, we're going to have three different inputs. We're going to have AI, which is going to be the ith bit for the first number. We're going to have BI, which is going to be the ith bit for the second number. And then we're going to have CI, which is our carry bit. And then we're going to have two different outputs. We're going to have SI, which is going to be the sum bit, the sum of AI and BI. And then we're going to have CI plus 1. And this is going to be the new carry bit that goes to the next column. So if we have a number that needs to carry over to the next digit or next set of digits, that's going to be stored in CI plus 1. The next step would be to construct our truth table. So this is what we would get. And if we take a look, this is basically giving us the inputs and outputs. So what happens when we add A, B, and C? So take a look at the first row, for example. So 1 plus 1 plus 1 it's going to be 1, 1. So our SI, our sum is going to be 1. And then our carry bit is going to be 1. And it's going to move on to the next column. If we have just 1, 1, and 0, then the sum of that is going to be 1, 0. So our sum bit's going to be 0. And we carry a 1 over to the next bit. And then so forth. So this is basically all the possible combinations of adding 3 bits together, which includes the carry bit, and lets us know what's going to be our sum bit and what's going to be our carry bit that moves on to the next digit. Let's now get the sub-expressions for the sum column. So you may need to go back, but there were 4 different ones in that column, which means that we're going to need 4 sub-expressions to handle those ones. And if we do all the work, I'll just kind of save the steps for you, but if we were to use the techniques we talked about before, where if we have a 1, we leave them alone. If there's any zeros, we would use the not operator to turn those zeros into ones. But we would get the following sub-expressions. We would get not AI and not BI and CI. We would have not AI and BI and not CI. We would have AI and not BI and not CI. It gets you get your tongue tied up pretty easily if you're not careful. And then we have AI and BI and CI. So these would be the 4 sub-expressions that we would get by turning all the zeros into ones by using the not operator. So we would combine these sub-expressions using the OR gates. So this would be this whole expression. So SI is going to be all 4 of those expressions, I should say sub-expressions technically, and combine them by using the OR operator. And then finally, we would get the circuit diagram for the sum output. And just so it makes it really simple, is if you take a look at the left side, we have AI, BI, and CI. So here are all of our inputs. There we go, there's our circle. Just to show where our inputs are. So if we follow through the paths, we would get the resulting sub-expression. So this line right here takes care of the result of one sub-expression. Here's the result of the next sub-expression. Here's the result of the next sub-expression. Here's the result of the 4th sub-expression. So we're using all the not and AND gates. So you can kind of follow through this and just convince yourself that these sub-expressions are in fact correct. And then finally, we would combine these using OR gates. So we have 3 different OR gates where we would finally get our sum result. And this would end up being the expression that we got previously. Now, we're not done yet. We just did the construction for the sum portion of the output. We still need to deal with the second output. We still need to deal with that carry bit. So if we look at that table again, we would see that we have 4 ones. So that means we need an additional 4 sub-expressions. I'm not going to list every single one of them, but you can take a look, use the same procedures before to get those 4 sub-expressions, and then we would combine them using the OR operator. So this will be the result that we would get. So CI plus 1 would be not AI and BI and CI, or AI and not BI and CI, or AI and BI and not CI, or AI and BI or CI. Here's the resulting circuit diagram for the carry bit. So once again, we have our input over here. And then if we just follow through with all the ands and or gates and not gates, we would get our 4 sub-expressions resulting here, 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 and here. So these are the results of using the and not gates, and then we would combine them to get the or gates, and then it gives the results of CI plus 1. And here is the final results of combining our 2 circuit diagrams that we had before. So this is the complete circuit diagram for the 1-add circuit. Now this looks pretty ugly, but it really is the combination of the 2 circuits we had before, just making sure we had enough space here to show everything. The layout here is just a little bit different. Our input is now down at the bottom. It's down here. So here's our AI, BI, and CI. And what we have here is a vertical line for the positive version of the 1 value for them. And also we have a NOT gate for the opposite. So we can get 1s and 0s for these. So we have our NOT gates right here. So that way our vertical lines give us AI, not AI, BI, not BI, CI, and not CI. And then we can take care of the rest of the circuits accordingly, as we've discussed before. So we have all 8 possible combinations of the possible things we can get for AI, BI, and CI, whether they're 1s or 0s. But this sure enough does give us the complete circuit for 1-add. We'll now show the complete full adder circuit. And notice that we have these 1-add circuits in here. So these would be the same circuits that we just showed, except instead of drawing that entire diagram again, we'll just draw a box and say, here's our 1-add circuit. Then we can understand what's going on there. It does add the respective bits for a particular column in our numbers. But what we have up here are the inputs A. So here's the n-bit value for A. Here is the n-bit value for B. So what we do here is that we send the respective values or the respective bits for each value into one of these 1-add circuits. So like for example, let's take a look at the rightmost 1-add circuit. So we input A0 and B0, and then the initial carry bit C is going to be also 0. So we have our 3 inputs for AI, BI, and CI. And the output is going to be S0, which is done down here, which, by the way, this whole thing right here is the resulting sum of A and B. And then we also have C1, which in this case would have been CI plus 1. That's going to be our carry bit that gets sent as input to the next 1-add circuit. So we just repeat this for each column when we add the respective digits of A and B. But this sure enough when we get to the far end, so when we go from right to left, so this final 1-add circuit here is going to give us the final result. So it's going to output Sn minus 1, the sum there, and then our carry bit is going to be added to the end of our sum. But this sure enough will give us the complete sum of adding A and B.